Welcome everyone to my talk, Filecoin and GPUs. So the goal of this talk is that you get an idea about how the process of creating a proof of replication is, and that you get a good understanding of which parts work great on the GPU and which are not, which should be done on the CPU, and especially for the parts for the GPU that you roughly know how they work. But before I get into the details, as this is an event celebrating Filecoin for 1 year, I also like to show you the progress. So I've run the proof of replication on some hardware, and so the same hardware from a version a year ago and the version that we have today. And as you can see, the version a year ago for sealing a 32 gigabyte sector took about 3 hours. And now we are down to about 2.5 hours, which is a great improvement. All the details about this graph will come later again. So this is just to get you excited. So if I talk about Filecoin, I mean proofs in this talk, because Filecoin means many different things to different people. So sometimes people refer it to as the protocol or as the cryptocurrency, or sometimes as the implementation like Lotus. But in this talk, I mean the proofs as in proof of replication and proof of space-time. As this talk is about GPUs, I also quickly like to talk about what GPUs are good for. So if you have huge amounts of data and you have some operation that you can apply to the data in parallel and crunch through it basically in one step, that's good for GPUs. What they are not good at is if you have some interdependencies. And then we would probably just get back to the CPU. And Filecoin actually has both those things. So we have things that are intentionally not parallelizable, so they run on the CPU, and we have parts that we want to move out to the GPU in order to improve the performance. So this talk concentrates on the POREP, the proof of replication. Sadly, I don't have the time to talk about the proof of space-time. So the proof of replication is also known as sealing and has 4 phases. 2 big ones. So we make the difference between the pre-commit, which I would call the preparations, and then there's the commit, which is about the actual proofs. And as you can see, those phases again split into pieces. And the important thing here is now that we have kind of like a CPU heavy phase and we have a GPU heavy phase. But now I will get into the detail through all those 4 phases. So let's start with the pre-commit phase 1. This is about SDR. SDR stands for stack depth robust, and it's about encoding. So what we do here is we take the original data and encode it in a unique way. And here the important bit is the unique, because if you do the process again on the same data, you will get another replica copy that is again unique. And this is part of the whole process because we want that people store unique copies of the data. And this step is not parallelizable by design. So it runs on the CPU and it takes quite a lot of time. What it does in the background is mostly it's reading a lot of data from disk, then it's doing some SHA hashing and writing those hashes again. But the point why it's not parallelizable is that the hashing, you often depend on previous hashes to hash the new hashes. So therefore, you have those interdependencies. And in this step, there's also some basic tree building, which isn't really performance critical, but tree building is kind of core to the proof of replication. Therefore, I want to briefly talk about what Merkel tree building means. So what is a Merkel tree? Here, you can see an example. So at the bottom, you have your data you want to build your Merkel tree on. And what you do is you have a certain number of children. In this case, it's 2 children. So we call this the arity of the tree. In Filecoin, we also have trees which have, for example, 8 children. But in this case, it's only 2 children. And so you take 2 pieces and hash them together. And then you have a parent node. And you do this with all your data, and you have then several parent nodes. And then you again hash those parent nodes to get new parent nodes. And in the end, you have the root node with 2 children, which is basically the hash of all your data. So why is this interesting, or like why would you do this? There's something called Merkel inclusion proof. And what you can do with this is, if you want to prove that certain bytes are part of your data, you would normally transmit the full file and look into the file. But this is not really efficient. So what you want to do instead is that you only transmit a proof, a Merkel proof. And here you can see in the light gray boxes that this is what you would need to transmit. It's only a subset of the tree. And what it actually is the parents of the F in this example and the siblings. And with all this information, you can then verify that F is really part of the data. Let's get to the next phase. It's the pre-commit phase 2. It's about Poseidon hashing. So again, we do some Merkel tree creation. This time, several ones. I won't go into the details, but the important bits is we use Poseidon hashing for this. Poseidon hashing is a hash algorithm that works on finite field elements. What they are, well, they are a cryptographic primitive. That's all you need to know for now. I will get back to this later. And those this cryptographic primitive is used in Snarks, which I also get to back later. And they are just better than or more efficient than working with SHA hashes. And there, the tree building is highly parallelizable. So therefore, we do it on the GPU. So I will get to the exact steps. So first of all, for the Poseidon hashing, you need to initialize it with some constants. This is just done once. If you start the proof system, it's done once. So you just do it on the CPU. Then something happens in kind of a loop. So if you think about the previous example with the Merkel tree. So you see at the bottom, you have lots of data. And you then take, let's say it's really a huge amount of data, which is bigger than the memory of your GPU. So let's say you take a third of the data and you batch it up, and then you put it on your GPU. And on the GPU, it can then do this parent calculation of all the elements in parallel. So it's very good for GPUs. And once we have those parents, what you're then going to do is that you then return them and you create the next batch into the calculation. So it means that in this step, we do the actual tree building, and the tree logic and the batching is all done on the CPU. And only the actual hashing is done on the GPU. So only a small part. Let's get to the next stage, the commit phase 1. This is about Merkel inclusion proofs. So we create those in order to make sure that this replica data that we created contains the same data as the original input. And this is a really fast process. So on a beefy machine, it takes less than a second. So therefore, we just do it on the CPU. There's no point of putting something on the GPU if it's that fast. And finally, we have the commit phase 2, which is about Snarks. And first, I would like to talk about like why do we need another phase, because we have already like proofs to prove that the replica is the same as the original data. The reason is that those Merkel proofs are quite large, and it wouldn't be feasible to putting them on chain. So what we do instead is we use Snarks in order to make those proofs smaller so we can put them on chain. And now you probably want to like, what are Snarks? Like, what is this? So that's probably, I could talk for hours and hours trying to explain what they are. I think, to me, Snarks is this magic cryptographic black box that does some magic things and contains lots of cryptographic primitives. I will go into some bits of it, but not all details. This would then be a separate talk. So what you do is you build something called a circuit. That's kind of, I mean, it's still software, but I would say it's basically the physical representation of a system that does some magic things. And those are basically polynomials, as you know them from school or university. And you have lots and lots of them, really a lot. And all those operations that you do in those Snarks happen in finite fields. So you need finite field arithmetics, because it's also working on elliptic curves and so on. So now we get back what I earlier said is about the Poseidon hashing. So Poseidon hashing is native to finite fields. So therefore it's a good fit for those Snarks. So what's now actually running on the GPU? So what we want to do is, if in the system, we want to evaluate those polynomials at random points, which means basically we want to get out the results. So you would have, as you can see at the bottom, like such a formula, and you can do it with pen and paper, and you just want to put in some value for the x, and you have some values for the a's, and then you do a calculation and get some result back. This is what evaluation means. And we want to do this efficiently on the GPU. So first, what we do is something called inverse fast Fourier transform. And what it does is, so the problem is that in the circuit, those polynomials are represented in a certain way, but to do the actual calculation, we need to represent them in a different way. We actually need to transform them into a coefficient representation, which is the one that you can see at the bottom, and most people are used to or think about when they talk about polynomials. So we do this transformation first, and this is again an operation that is parallelizable because you do some divide and conquer algorithm, and you then recursively step through those things, and in the end you get the coefficients back, which is those a's in the polynomials. And the other thing is then, if you actually want to evaluate this polynomial, you use a function called multi-exp. So what it does is that it now can operate on many of those elements at the same time. So here is, I've put the kind of like the function call. So you put in the coefficients and you put in the x. So the x, so those things are then really like concrete values and not variables anymore. And then you kind of do this calculation in one big step on the GPU and you get the result back. So to recap, the parts that run on the GPU is from the whole process of creating the replica and sealing and creating the proofs. It's actually only the Poseidon hashing, the fast Fourier transform, and the multi-exp. So let's look into what it means and what performance improvement it gives you. So This is again run on the same machine as from the first slide. And now you hopefully have a better understanding of what those bars mean. So let's look into detail. So at the top, we have the CPU runtime of a proof of replication of a 32 gigabyte sector. And in the bottom, we have, if we have the GPUs enabled. On this machine, we even had 2 GPUs. So what you can see is the pre-commit phase 1, which I named SDR encoding, is the same on both. As I mentioned, it runs on the CPU. It doesn't use a GPU at all. So therefore, it totally makes sense that this runtime is the same. And it takes a lot of time. It's about 2 hours. The next phase is the pre-commit 2, which is about Poseidon hashing. And there we use the GPU, as you remember. And we can clearly see here, like on the CPU, it takes something like, let's see, like almost an hour, like 45 minutes. But if you use the power of GPUs, it's a matter of 10, 12 minutes. And the next phase, the commit 1, which is the Merkel inclusion proofs, you can't actually see it on this diagram. As I mentioned, it takes basically less than a second. So therefore, you can't see it in this diagram. And it's for both. It's just both cases. It's just this fast. And then finally, we have the commit phase 2, which is the Snark magic. And again, we can see that if you run it only on the CPU, it would take over an hour. And then it's a matter of 15 minutes or so. So you can see it really improves the performance a lot if we use the power of GPUs. And now, finally, I'd like to talk about what we use underneath. So the proving system I was talking about is programmed in a programming language called Rust. And of course, we use libraries for certain things. And I'd like to get into some of them, the important ones. So we interact with OpenCL, and there is a library called OpenCL3, which is well maintained, and it actually replaces a library that is no longer maintained called OCL. So we've used OCL in the past, but with newer versions of the proofs, we use OpenCL3. And as you've probably seen, the transition was quite seamless. Probably you haven't had any problems with it. And what I'm especially proud of is that CryptoComputeLab helped in the early stages of getting OpenCL3 polished, because it was still quite young, but we've bet on it, and it was a good decision to spend some time on it and improving it and make it work for our use case and also make it work for other people. So now it's really like a general purpose library and not only for Filecoin. It can be used by anyone. And it's also its intention. On the CUDA side, it doesn't look that happy. The Rust CUDA library is only partially maintained. And currently we even need to use a fork of it, but it should be short-lived. It's just a single function, and I hope to get it upstreamed because I really don't want to maintain a fork of it. Then we also, of course, with the most recent version of Lotus in the proof system, what you can do is you can switch between OpenCL and CUDA. And so we have code for OpenCL and CUDA. And of course, you don't want to code everything twice. So we've built an abstraction library to make this easier for you. This is, again, not Filecoin specific, but general purpose. So if you have those needs, have a look. And finally, there's a library called EasyGPU, which is for finite field arithmetic over prime fields and elliptic curve arithmetic. And what this is about is it's highly optimized code for GPUs. And we want to make it, again, like also usable for other people outside of Filecoin. And currently, it doesn't contain FFT and multi-X that I've presented, but the plan is to move from some other library to move it into that library, so that people that need those functions can just use this library and don't depend on many other libraries or Filecoin specific stuff. All right, that's all I have for today. Thanks everyone for your attention.